Hey everyone, so this is the JavaScript runtime visualized. So I'm going to explain what the JavaScript runtime is and how it allows for efficient programs, and then I'm going to show it to you in real time within my project daily set. So here's how it works. Essentially, you have multiple components that are working together, and these components, when they're working in unison, is the JavaScript runtime. So the components are as follows: call stack, web API, event loop, priority queue, and callback queue. All right. So here's how it works. Essentially, when you have a function in JavaScript, it gets put into the call stack. So let's say you had console.log, like over here, right? That would be added onto the call stack. All right. Now, within a function, if you have any other functions that are nested within a parent function, those functions would also be put into the call stack. Now, no other functions other than the nested functions and the main function itself can be put into the call stack. So until the execution of these functions are finished, no other functions can be added. All right. Albeit, as I said before, nested functions are allowed. So an example of nested functions would actually be this over here. Um, in this case, right, where you have a function of handle submit, but then within that function, you also have handle submit question. So that handle submit question is nested within the parent function of the handle submit. So both of these would be added to the call stack because handle submit question is not an independent function. It is nested and dependent on the execution of the handle submit. Anyways, back to our visualization here. Now that you understand a bit more about the call stack, essentially, once the execution of these functions are finished, the call stack pops those functions out. All right. So it releases those functions, and therefore the call stack becomes cleared. But here's a problem with only having a call stack, right? What happens is you if you have functions or tasks that take a long time, for example IO bound tasks, which are communication between different softwares, well then these tasks will have to finish their execution fully before other tasks start. That means that your file and your program is blocked in execution to that task, and other tasks which now might be related but can help enhance the user experience cannot be shown until that lengthy task finishes its execution. So that's why we actually have the event loop and the web APIs and the callback and priority queue. All right. So here's how it works. Essentially, the call stack is the logger or the record of all the functions that are being executed. If a function is going to take a long time, an asynchronous function, all right, this means it would disrupt the normal flow of the program, wherein it would not go step by step. It would actually hang on a step for too long, and so therefore it blocks the rest of the steps and tasks within your code. Well, then what would happen is this task, which would hang the whole execution, it would be sent into either the callback queue or it would be sent into the web API. All right. In the case of Node.js, it would be sent into libuv, which is uh, this software which works on a server-side environment. But if you're working on client-side JavaScript code, which I am, it goes to web APIs, which directly interacts with the browser. All right. So essentially, that function, its main logic is given to the web APIs. All right. So for example, like fetch, right, which fetches an API, which is going to take some time. That would be sent to the web API to finish execution. And then that function itself within the call stack would be popped out because its job is finished, right? Its job was simply to give that the execution of that function to the web API. Now the web API will do its thing in the background, in the back burner, right? Whilst the call stack can continue its execution. So it can take on more functions now since it's cleared, right? Um, because that main function is gone, and so it can just keep doing its own thing, so the user doesn't experience any sort of disruption while that's happening, right? And the web API is just finishing its fetch. Now let's say like after 50 milliseconds or 100 milliseconds, you get your response back. All right. What would happen is the callback function. So within these asynchronous functions, you have a callback function, which is essentially something you want to do after the fact of execution. Well, those would need to be put back into the call stack to be called, right? But the thing is that call stack is immutable, meaning that you cannot actually directly change or add anything to the call stack. It needs to happen through the execution and the compiler itself. So how's the web API supposed to add this function, this callback function, into the call stack itself? Well, it does this through a queue. Specifically, there are two: the callback queue or the task queue, and the priority queue or the micro task queue. So essentially, what happens is, let's say after the fetch, right? You have a callback function which logs success in fetching API. Well, this will be sent to the callback queue, all right, or the task queue. Now, once it's sent here, when the call stack is completely cleared, right? It's ready for new tasks. Well, then the event loop will basically take that function, the callback function, and populate it into the call stack so that's ready for execution again. All right. And so this would happen step by step for each of the pending callback functions. Now the priority queue or the microtask queue does the exact same thing as the callback queue or the task queue. I'm just going to call them by callback and priority. But just remember, callback queue can be interchanged with task queue, and priority queue can be interchanged with microtask queue. Now, as I said before, the priority queue does the exact same thing as a callback queue. But the only difference is that a priority queue is reserved for promises. All right. So in JavaScript, we have a promise, which is basically a function that is expected to return something. It doesn't have it immediately upon execution, but after some time, it is expected to have have a response, whether that be an error or the actual result of the logic itself. So those callback functions, which belong to a promise, they're added to the priority queue, and they have first dibs essentially for being added into the call stack. So before the callback queue can populate the call stack with its functions that need to be executed in the engine, in the JavaScript engine, the priority queue adds its task first. All right. Now, this whole architecture is built in a way so that now, for example, if you have to fetch an API, which is expected to take a long time, that is offloaded to the web API in client side and libuv in Node.js, and then essentially, um, it'll happen in the background, like the browser would take care of it, or the libuv program would take care of it, right? And while it's happening, the call stack can continue its execution, right? It can continue doing other things. Once this is done, let's say the fetch is done, well, then that callback is added to one of these queues, depending on if it was a promise or just a regular asynchronous function. And then after all of that, the callback function, once the call stack uh, is empty, the callback function is added onto the call stack itself. So that was a little summary of exactly what's going on within the JavaScript runtime. So when you hear the event loop, like JavaScript event loop, that's only one component within this whole architecture that allows us to ensure efficient programs. Because now you can have other things running while more intensive tasks, which are going to take a long time, can do their own thing in the background, right? But please note, this does not really affect CPU intensive processes. It's more about IO bound tasks. Now, let's see the code example that I was talking about. So here it is. It's actually the handle submit within my daily sat code. This is all open source, so you can check it out yourself. It's within the source component, and specifically within components, features, and then practice. All right. And it's question content.tsx. Although I might be refactoring this because it is a really big component, bigger than I would be comfortable with. And it doesn't really follow the single responsibility principle in React too much. So I'm probably going to refactor it, but I'll update this description if I do so. Anyways, so this function handles the submission logic for a question. So when you click submit on the daily side practice platform, you're really just propagating this function here. And within this function, you have some simple things, some simple tasks, which are not expected to take too long. It's like maybe 1 millisecond at most, right? It's pretty fast, right? But then we get to handle submit question. Now, see, handle submit question, if I were to open this, is actually a server action. You can see it's within the server action file, which is part of our lib file. So if I just go ahead and open my lib file here, go to server actions and here, all right. So you can see this is the code for the handle submit question. It's just a Next.js server action, right? Um, and essentially what it does is it connects to our MongoDB database, gets our session, and then it updates the user's values depending on what happened, right? So if they did win, right? For example, if they got it correct, then they would get an increase in their currency based off of the constant points that everybody makes, and then their investor reward bonus, which is part of our shopping feature. But let's say if they didn't get it correct, then they're not going to get this. But there's still going to be an operation of incrementing the wrong answered count, right? So there's still a lot of operations happening within this code. So, anyways, if I go back into our question content, this is the front end. That was the back end because it does use the use server directive, which basically forces this file to run on server side rather than client. So you can access environment variables without the next underscore public directive as well, making it more secure. Anyways, let me go back over here. So within our client code, if I go back to our handle submit, essentially what's happening here is this handle submit is being called. But this handle submit is an asynchronous function. If you didn't notice, I marked this with the async um, part over here. And that's because it is an asynchronous function, right? And server actions actually by default are supposed to be marked with asynchronous. So anyways, back in this code, that means that this is actually a promise because all asynchronous functions, they are actually promises. So I can use the dot then, the dot catch, all of these things, right? And that's exactly what I did here, all right? And by doing so, essentially what this is saying is that put this into offload this into the web API, right? Let that run in the web API or in a external process in another software, right? And whilst that's being offloaded, continue with the rest of my tasks. So in this case, I have some front end logic which I'm updating here. So continue with these tasks while this is running in the background. Now once this is done, then run a dependent task, so a task that's dependent on the execution, the completion of this function, which is this over here, the toast.success or the toast.error. But now, if I were to update this and add an await, so if I were to edit this file here, right? And instead of doing this, if I added an await here, like like so, right? It's first of all going to run into an error because I need to make this asynchronous so that the await can actually even be called. And secondly, what this would do is essentially block the execution. All right. So it would basically do the complete opposite of what we were kind of talking about before. It would wait until this whole execution is done before moving on to the next bits of the operation. All right. But in my case, I don't want to do that. You could do that if you need to, right? If your application logic calls on it. But in my case, I don't need to do that. And the reason for that is because these things right? These front-end logics are not dependent on this operation here. So this can happen whilst this is operating in the back burner. All right. So essentially, that is the JavaScript runtime for you, explained pretty deeply.